Hello everyone, welcome to the online heat power engineering class. This is unit 4 and session 5. So here in this session, let us solve some problems with the Carnot cycle. So in the previous two sessions, we have discussed with two cycles. One is Carnot cycle and one more is Otto cycle. Okay, so in this session, let us solve the problem of Carnot cycle. So before coming to attending this session, please be ready with your notebook, pen, as well as a calculator. Okay, so I'll dictate the problem, you note it down. A Carnot engine working between 650 Kelvin and 310 Kelvin produces 150 kilojoules of work. Full stop. Find thermal efficiency and heat added during the process. So now you read the problem once again and write down the given data. So the engine works between two sources, which is 650K and 310K. So the T1 is equal to initial temperature, which is 650 Kelvin, and the final temperature, that is a T3, which is equal to 310 Kelvin. So where W is equal to 150 kilojoule, that is work. Okay. The solution part, we know that thermal efficiency, that is equal to T1 minus T3 divided by T1. So here it is 650 minus 310 divided by 650, that is equal to 0.523, or you can say it as 52.3. Very easy. We know that the heat added during the process Q122, that is equal to work done divided by efficiency, because normally what we can say, efficiency is equal to work done divided by heat added. So you can rearrange that equation, and from that equation you can come to know that the heat added, that is equal to work done divided by the efficiency. So work done he has given, that is 150 kilojoules divided by the efficiency, which you have been already calculated, that is 0.523. And if you calculate, if you solve this puzzle, you can get 286.8 kilojoules of heat as going to added. Is that okay? So this is a first problem. And now take down the next problem, that is problem number 2. A Carnot engine operates between two reservoirs at a temperature T1 and T3. The work output of the engine is 0.6 times the heat rejected. The work output of the engine is 0.6 times the heat rejected. The difference in temperatures between the source and the sink is 200 degrees centigrade. Calculate the thermal efficiency, source temperature and sink temperature. Calculate thermal efficiency, source temperature and sink temperature. There are 3 unknown data. Okay. And now write down the given data. What and all he has given? W is equal to 0.6 into heat rejected, right? He has given the work output of the engine, work output W is equal to 0.6 times the heat rejected. That is equal to 0.6 Q324. If you see the Carnot cycle, so heat rejected is Q324. So T1 minus T3, difference between the reservoir, temperature difference between the reservoir, that is T1 minus T3, that is equal to 200 degree centigrade. 200 degree centigrade. And the solution, you can say, solution is, first one, what you have to calculate? You have to calculate thermal efficiency. So let us start with the thermal efficiency. Thermal efficiency is equal to what? We know that it is a ratio of work done to heat supplied. So based on this, you can rewrite this equation as work done divided by work done plus heat rejected. Work done plus heat rejected, because work done is equal to what? Work done is equal to heat added minus heat rejected. So heat added minus heat rejected plus heat rejected. Heat rejected getting cancelled and only heat supplied remains. So again it stands efficiency is equal to work done divided by heat supplied. So this is equal to, you know that the work done is equal to 0.6 Q324 as already given, divided by work done is equal to again the same equation, same value 0.6 Q324 plus heat rejected that is Q324. Heat rejected that is Q324. So that is equal to, see, Q324 is common here. So ultimately what remains? 0.6 divided by 0.6 plus 1. Here it is 1 plus 1.6. So if you simplify this, you will get 0.7375 or 37.5%. You can use your calculator to calculate or to solve this problem. Okay, so please check the answer with your calculator. Now I'll continue with the second unknown data, which is source and sink temperature. Let T1 be the source temperature and T3 be the sink temperature. Consider T1 is equal to source temperature and T3 is equal to sink temperature. We know that the thermal efficiency that is equal to T1 minus T3 divided by T1. So efficiency value we already discovered it, 0.375. That is equal to T1 minus T3 divided by T1. So that is equal to, see, T1 minus T3 is equal to the what? It is a temperature difference between source and sink. That is already given somewhere here. Yeah, see here. It is 200 degrees centigrade. So that is equal to 200. I'll add the value of T1 minus T3 divided by T1. Okay. So now you can simplify this. You have 0.375, that is equal to 200 by T1. If you cross multiply this, what happens? 0.375 T1, that is equal to 200. So T1 is equal to 200 divided by 0.375. That if you simplify this by using your calculator, which will give you 533.3 Kelvin, that is equal to 260.3 degree centigrade. If you can convert from Kelvin to centigrade, minus 273. Okay, use your calculator and you cross check the answer. And T3 is equal to T1 minus 200, that is equal to 260.3 minus 200. So that will give you 60.3. So where T1 is equal to source temperature, T3 is equal to sink temperature. One is hot body and one more is cold body. So these are all the answers for this problem. So I repeat, thermal efficiency, the unknown data thermal efficiency, that is equal to 37.5%, which you have been calculated, and the source temperature T1 is equal to 260.3 degrees centigrade. Sink temperature T3 is equal to 60.3 degree centigrade. Okay, so this will ended with the session 5 of unit 5. Thank you so much. Let us meet with the next session by solving the problems related to Otto cycle. Thank you so much.